this out here. Okay, so, all right, remember we went over this linear correlation information. So I have this worksheet online for you guys that defines everything like we've gone through. And here's a formula that we've written on the board and that we use, right?
You can't see anything.
That's bizarre. Why can't you guys see? Okay, there we go. Thank you. That'll help. So here's our linear correlation coefficient formula, right? And so it's on the board, but we've been using this formula. And we have all the information there. So I want to go through, and I have here too a demonstration of the whole process of this for you, so you guys can notate this as well, right? We have a test statistic, right? So T with this test statistic formula. And remember, your degree of freedom is n minus 2. And you're going to set up your hypotheses this way here, where rho is 0, rho is not 0. We went through that already. And you have here your decision rule. So if you guys remember that, here's your decision rule. Okay? So notice again, you have critical values that you need. So here's your format that you went through last week. Critical values. This is always going to be a two-tailed test. Anyway. And I do have an example here of data. We'll go through some of these here first, but I think what I want to do first is go all the way down here. This is an example of all the steps that we went through last week. So I won't go through that example again. And you guys can look at this over and look at step 3, how the computation went. We found that there's a linear coefficient correlation value, linear correlation value here. Let's go back. Of R being about negative 0.944. We punched this in our test statistic, and we got a value of negative 6.398. And in relation to our decision rule, back up here, it looks like that particular value of negative 6, right, was out here. So they wanted us to reject the null. If we reject the null in that case, we find that, there is a linear correlation. So this is kind of a review of what we did last time. So all those notes are online with this particular example. Now you have problem sets here. I got problem 1 where you have to compute this linear correlation. You got to compute the test statistic and, of course, see where it lands in your decision rule that's up here. So for every problem, we have that information for you guys. And I went through and I created problem 4 all the way down to, I gave you some space. I think I gave you about 8 problems to do. 7, 8. Going through the format of your example. So we already did this. So where we're at now is to look at this regression line. And what I gave you guys earlier here was how to obtain the slope and the y-intercept. So notice we need to find when there is a linear correlation, we want to find the best fit line. It's that y equals mx plus b. This is what we're going to use. So as you can see again, and remember that you have all the information from the table, right? Sum xy, sum x, sum y, sum x squared, sum x to the second power. You have your sample size. So you're going to need this information again from the original table to compute your slope. And then you need some y, you need that slope value, you need some x and the sample size, and then you can get your y-intercept now. So that's what we're going to do, and that's where we're at. We're finding the slope and the y-intercept. It's all on the board again. But let's actually do the following. Now remember, you're trying to get this equation. And that's the same as saying, y equals b plus mx, which is actually just y is mx plus b here. So let's try this here. And I gave you some more definitions that I started to give you. Okay? And you could use this second option. You can find r, we can find sy and sx. This is what they are: standard deviation with the x variable, standard deviation with the y variable. And once we get that, and this is my slope m, and then here we can get b by just saying we need the mean of y minus that slope m value times the mean of x. So b here, and this is another formula that's used to find the b value. So there's different formulas here that you can approach this with. So anyway, let's go through this example 1 here. And in example 1, I do have this here for you guys. You have the data here. So as you can see, they didn't actually give you any particular situation. They just wanted to see if you could do the mechanics. Here's an x variable, here's a y variable, and there's your pair of data, x and y, right? And again, these notes are going to be, they're online, I believe, already, so it should be there. And then you have your scatter plot. So remember, you're looking at the data. Now, does it look like that data can fit along a line? What do you guys think? It looks to me it can. So because it looks like that data can fit along a line, what are we going to do again? We're going to try to test this to see whether there's a linear correlation. So we looked at the scatter plot. It's right here. And by the way, that line might look like it'll be a negative slope. So let's try to find out. And so here's the example of what I'm talking about. What happens here is we need, like we mentioned, the xy column, we need the x squared column, we need the y squared column, right? We already have the x column, we already have the y column. So what you'll end up doing now for each one of these is determining the sum. Is that right? So that's why I have a sum here. And so you have here 66. Remember, that's the sum of the what? Of the x values. What's 55? Sum of the y's. Good. Good job. What's 690? Sum of xy. What's the 950? Sum of x squared. Because that's the column it's in. Is that right? And then what's this 625? That's sum of the y squared column because that's the column it's in. So we just have to identify those things, and it's just going to be about us punching all this stuff in our calculator here. Okay, and so what I did was, notice again, there's 1, 2, 3, 4, 5. Is that true? There's 5. How many data values? 5 data values. Is that right? So n here is what? 5. So what we do here is our linear correlation coefficient, R, because it's based on a sample here, I plug in all the values. So let's make sure. We do have 5. Sum xy is 690 minus, looks like we have sum x, 66, sum y, 55. Good. The numerator's okay. Now divided by 2 radicals. So again, we have 5, and then sum x squared was 950. Good. Minus sum x to the second power. So there's a 66 here. And don't forget that the power down here is 2. Okay, so we have that power down there too. Let's put it in red here. And then let's double check if we have 5 again. Now we have sum y squared, and that's going to be 625 minus sum y, which is what? Oh, 55, sorry. And then what do we do? What power is there going to be there? There's a 2 power there. So anyway. And then when you punch this in your calculator, we get that the R value is negative 0.907. So there's your linear correlation coefficient. That's all the values you plug in. And then you plug that value in here, your test statistic. And so here's that value for R. And it goes down in here. Now 5 minus 2 in the denominator, that's your degree of freedom. So this value here is going to be 3 in your calculator, 5 minus 2. And we get a test statistic to be negative 3.730. So this is everything we did last time, And we go, okay, what does that mean? Well, on our decision rule, because we're going to assume here that alpha, let's write this down. If you read the example, alpha is 5%. Of course, it's with two tails. Your sample size is 5, so that degree of freedom is going to be 5 minus 2. Is that right? For linear correlation, it's n minus 2. So I have my 5%, my degree of freedom. You're looking at a t table, small sample, right?
Isn't it negative, minus 1 for the degree of freedom?
Not for linear correlation, it's minus 2. Okay? And so, if you check your t table, you'll find negative 3.82, positive 3.82. This is our critical values. Okay? Don't forget degree of freedom is going to be what here? 3. Okay? So, what was the test statistic value again? Negative 3.730. So, that is to the left of negative 3.182. So, your test statistic is out here. Is that true? Because this is where negative 3.730 would be. Now, that value is in what neighborhood? Yeah, what neighborhood is that in? Reject the what? The null. So when we reject the null, say goodbye null. Sure enough, what do we know? There is a linear what? Correlation. All right, so sure enough, that data can fit a line here. Yes?
If you go back on your notes, on the 27, you did show that the degree of freedom was minus 1, not minus 2.
I believe it's minus 2. Let's double check. Put it all the way up here. Yeah.
Minus 2 or minus 1?
Minus 2.
It's minus 2, is that right?
Yes.
It's minus 2. So let's double check there. It's going to be minus 2 here. Degree of freedom. You have 10.1.
Something was here with the.
What's that?
I do understand you guys' concern. Yes. For linear correlation only, it's n minus 2. All right? So it's a different degree of freedom. This is only for linear correlation. All right. Yeah, I know. Don't worry. I see your point. I see your guys' concern. You go, wait a minute. With all the others, it was n minus 1. You're absolutely right. So you're not losing your mind. Okay, but for linear correlation, what's it going to be? N minus what? 2 there. Good job. Okay. So anyway, so we're at the step where, let's go all the way back down here. Okay, yeah, I understand your concern. All right. Okay, so for linear correlation, degree of freedom is 3. Okay, for the other hypothesis testing, yes, degree of freedom is 1. For the chi-square distribution, for the t-table, it is n minus 1 for the others, but not for this one. All right, now let's double check here. So we know that there is a linear correlation. So what you would do now, ladies and gentlemen, is you'd go here, and we're going to try to find the best fit what? Trying to find that best fit line. Okay, you're going to find that best fit line here. Now, for the best fit line, remember, we need that slope here first. This is my M, okay, and this is the B. So for the slope M and this B, notice we're going to use the N here. N is 5, so it's right here. We need the sum xy. So if we go back, we have to go back to the table. What's sum xy? Is that 690? Okay, so let's double check if that's here. This is sum xy. That's 690. Okay, and then you're going to subtract sum x and sum y. So if we go back and find what that would be, sum x, go back to your original table here. Sum x is 66. So we're looking at this, and that's 66. And then sum y is going to be 55. Is that right?
Yes.
All right, so let's pink maybe. There you guys go. So that's your numerator. Now don't forget in the bottom there we have n is 5, so that was in red. And then sum x squared. Well, we don't have that one yet. So let's paint it green maybe. So sum x squared here is 950, is that right? So, sure enough, sum x squared is 950. And then that's minus sum x in parentheses squared. So, oh, it's the lighter green. So that better be 66 squared. Raising this to the second power here, right? So you have a power 2. It's a power 2 there. So when you plug all these values in, notice what you end up with. We end up with a value here of a negative 0.457. So I want to say to you guys, negative 0.457 here, that's our slope value. And the way they wrote it is they put the slope over here, okay? They put that B1, that's our slope. So notice that it's right here. It's negative and it's 0.457, multiplied the x variable. What we also need is that B value. And so to get the B value, according to your book again, we need to follow this formula here. We need the sum y, and I think the sum y was in pink. Remember this? 55. Sum x squared is dark green. So we forgot to color it over here. This is a sum x squared. Right, so sum x squared should be 950. Sure enough, it is. Minus sum x. Sum x was lighter green. So this was lighter green, and that was 66. And then we have sum xy. Well, sum xy, we colored it blue, right? And that was 690 here. So there's your numerator. You plug those values in. We need n again, and let's go back. And we had colored that red, so n is 5. So we're right there looking at n. Same n here. What about sum x squared? Sum x squared we know was that dark green. So let's double check. Was it 950? It's 950. And then that sum x again was in light green, right? We have it right here, sum x. That should be 66, and it is. And then don't forget, what do you do with that power now? That's raised to the what? Second power. So when you go and you punch that in, notice you get now a 17.030. And that value is going to be my y-intercept value. So if you really wanted to write this in terms of an algebra equation here, that's y equals negative 0.457x plus that 17.030. So like I said, what you're going to do now with this today is you got to punch these values in your calculator to compute the slope and compute your y-intercept again. All right, you guys okay with that?
Where can we find this in?
Say that again. Where can you find what?
This.
Well, it should be on my website. Let's double check here. Math 227. 227. Double check here. If it's not, let's make. Oh, sorry, wrong link. 227 should be in your video site here. Video library. Nope, that's the old one. So let's look at your video library here. Go all the way down to linear correlation. This is slow. All right, let's see. Oh, well, no, let me double check here. Okay, I'll make sure I put that there tonight when we get there. I have a different, there is notes there on it, but it's a different set of notes. So I'm going to put both set of notes. I have the old notes, and these are the new notes. So I'll put both. One is a PDF file. It's loading. It's about 2.4 megabytes, which is taking the school 10 minutes to load. And
are we going to find that in the video library?
Yeah, it's in the video library.
Under.
Yeah. So I do have some notes there too, with the same kind of notes. I'll put both of them. I'll put them, it's under Statistics Lecture 15. Okay, so I could see that there. Statistics Lecture 15 is where you'll see that. Now, let's try this here, this next example, all on our own. And again, it's going to be over generic variables x and y. Okay? And then you're going to have the other questions, 1 through 8, I guess, to do, and we can make that our assignment. We'll see how that works. Okay? You guys understand? Not only, I'll take it off of this here. Yeah. Okay? So, as you guys can see, yes, it's very color coordinated. It's all about you just punching this in and using your calculator, okay? So I'll show you the next kind of example of what I'm talking about. See, here's the summary of what we just said. You know that equation we just found? Y equals negative 0.457x. Now we have to add 0.17, or what was that? At 17.03. So what you guys are seeing here is the best fit line, this dotted line that I just showed that you have right here. Okay, maybe put that in red. This is the best fit line here. And as you can see, the data kind of follows that line. Okay, it's not perfect. It's not a perfect, what's called a perfect negative correlation, but it's close. So you can now use this to predict. You can use this equation, and that's the whole idea, that you have this linear equation, you can now plug in an x value and start to predict. Okay, and that's the whole point. So I even went through some examples here for you that says, okay, what happens now when x is going to be 9? When x is 9, we plug it in this equation, and we get y to be 12.917. And I say, what happens when x is 12? Okay, plug in 12, you get the y value being 11.546. What happens when x is 14? You plug in the 14, and you get y to be 10.632. And then what happens when x is 22? Well, plug in 22, you get y being 6.976. This is what we mean by being able to predict. And you're going to actually use an interval that's around this value, these values here. You're not going to use any other interval, but that's a whole other story, finding those intervals. But I won't give you questions that are outside that interval. So nevertheless, this is the idea behind the whole process of finding really whether, number one, there is a linear correlation. You test that by a hypothesis test. The second thing is, if there is a linear correlation, then you find the best fit line, and that is your best fit line. So this is the line they're looking for. This is the whole reason you're doing this, okay? Because you just found this what? This linear correlation, this best fit, also called the regression line. So as you can see, that data fits this line. Okay, you guys okay with that one? So now, I put in your notes here an option 2 using the algebra. Now, option 2, it uses the definitions like finding stuff like this. Here's my slope here. Option 2, let's change the color here. I have the R value. I need an option 2, the SY, that's the standard deviation for the Y variable. And this is, let's change that color to maybe green. That's the standard deviation for the X variable. So all I did here for us with this second option is to say, okay, my slope here, M, well, I already have the R value. Let's see. Colorblind, I guess what color did I use? Is that light purple? I guess I did use light purple. Or is that pink? Jeez. Is that pink? I guess I used pink. Remember, I'm colorblind. And blue, this is my standard deviation for what? For the Y variable. And then green, standard deviation here for the X variable. That gives me the same answer, if you guys notice here. So some people prefer this. I think I do, especially if you use a table like this. Then you notice that what we really found, here's the X variable. I guess let's use the dark green. Here's that X variable here. Oops. So for the X variable, here's my SX, standard deviation, for the X variable. For the Y variable in blue, here's what we use. And that's why the values are what you see here. R came from, our R linear correlation coefficient for the sample. And then once you get this value here, you have B. That's the mean for Y, and that's the mean for X, and this is my slope. So if you can see, I also have the mean here. So for X, 13.2. And that's why this value is 13.2. The mean for Y, we colored that blue. So here's Y, there's the mean there, and I guess it's a different blue. Where is that here? We're looking for the mean for Y. There it is, 11. Okay, because this is the Y variable now. The other was the X variable. And I just used all that information there. So I can get these values, the same kind of slope here, like I said, and I plugged it back here. Oh, I'm sorry, we're looking for the mean for Y. The mean for Y is in blue. Right here, right here. The mean for X is in green. All right, so there's the mean for X. It's right here. There you go. And as you can see, we got the same answer. So I went through all of this, looking at two sort of ways to plug these in, two sets of formulas, the ones I started to write down for you guys. And whatever you like to use. But anyway, just kind of curious, how many people like option, well, you'd have to compute this. Maybe you're used to option 1. But option 2, if you had like a spreadsheet, you could go that route too. So using a spreadsheet, I would say to you guys, this is the best for a spreadsheet. Without a spreadsheet, the other one is what we've been doing. So, yes.
I have a question.
Yeah.
So, on your first example, it was 17.030, and then this one is off by 1 point.
Yeah, very, very good question. Very
So
good
on your
question.
test, will you deduct points if it's off by 1 or 2
No, I'm not a surgeon like that.
Okay. Because
But,
I used your other equation.
yeah,
The shorter one divided by the sample size.
yeah.
And it's off by 2 points.
Which one are you looking at? I'm not sure the other equation for, which one over here?
The shorter one yeah.
Okay,
And that one's off by 2 instead of getting 17.030, I got 17.032.
I'll double check the calculation there, but generally speaking, whenever you approximate, it depends on where you approximate things. Well, I see what you got here, 17 for the y value,
Yeah.
y-intercept value. Okay, go back and see how we do that. For this here,
No, I used the other equation. I used the shorter one.
well, hold on. If you're going here, if you're talking about this value here, right, you're talking this one here, 17.030 for B. And you said you used a different equation to get B. Did you use the other one I gave you?
Yeah. The one
Okay, I see. I see what you mean. Yeah,
It's off
okay,
by
here's the
2
question.
points.
Let's write that down. B, I said to you guys, you could use sum y minus m sum x over n. Now, what'd you get for B here?
I got 17.032.
Good. Okay. All right, thank you. All right, let me say something here. You might say, Mr. Judge, which one is the best B? The best B that you have is this one right here. Now, you might say, but you said I can use this other formula. You can. And if you did that, I wouldn't mark things wrong. Okay? The reason it's different is because if you go over here, let me illustrate why this is a different answer. You see this m value in the shorter version for B? And that is a nicer version. I would probably use that version for B. That m you found where? Up here. And that was approximate. So the second you approximate, you throw data away. Okay, so when I give the answer of negative 0.457, and if you plug that in, you plugged in an approximate answer. But the original B value, we didn't approximate at that point. We approximated at the very end. So what I'm saying is, if you look at these over here, all this data here, for that B, never did we approximate. Only until we got the what? Final answer. So you had an approximation here, you had an approximation here. There's two approximations. The prior one, there's only one approximation. So what happens is, the more you approximate, the further away you go from the real answer. So because for the shortcut, you had two approximations to do, the first situation, only one. The first one is why I say is the most accurate answer. So yeah, if you keep approximating, you get further and further away. You propagate what's called an error. And that's something that happens with approximations anyway. Good question. Good question. Glad you did that. Anyway, let's try this out here. Okay, this is what that means. So you do this with a spreadsheet, you get the same answer. I'm wondering here now, let's go back here and see. That's example 1. Let's go back and see if we had example 2 here. I don't see an example 2. Yes?
So for the option 2, you had the mean and the standard deviation already. Are you gonna like give that to us?
Give what?
The standard deviation and the mean?
I give you the table.
So we have to figure it out.
So I would say to you, you would if you when do you use option 2? When you can get access to a spreadsheet. When would you use option 1? Well, for some of these things. So that's what I remarked, that you'll probably want to try option 1 here. Okay, so you're going to try to go the route for option 1. All right. Let's see. This is example 1. Let's see here in Excel here. Now, I have an example we could use here. Should we try this? Yeah, let's try it here. I know I don't have a blank space here for it. Let's see what we can do. First of all, let's try to get some of these things a little bit bigger. Okay. Did you guys see that better? Okay, let's try to see what we could do here with this. That's the XY column, is that right? We don't need caps. And then this is x to the what? Second, raise this shift, 2, and then we need a what? Y, shift, second power. Let's go back here. Okay, we got okay with that? So you might say, isn't this what we did last time? We're going to have to enter here. You have to enter this value raised to the second power. Is that right? And then,
Wait,
oh, sorry, you're absolutely right. Let's go back. We're going to take not that value. We're going to do this. The x times the y value. Is that right? Okay. Okay. Oops. Let's go down here. You know, this is what's supposed to do here. Nope, I don't want to write. I want to do autofill. Hey. Let's do autofill. Yeah. Autofill. Let's see what this does. No, fill. Let's do this. I think we'll try it that way. Get rid of the keyboard. Ah. All right, whatever. Ah, autofill. iPad, you are just a disappointment. Anybody know how to do autofill on an iPad? All right, now we do what here? Do the x variable. Now the y variable, raised to the second power, equals that y variable, raised to the second power. right, you guys okay with that? Now, hopefully we did it all okay. We need the sums here, so we got to put the summation formula. All right, now, Okay, I'm wondering here if there's any other degree of accuracy for this. All right. Whatever. Okay. So remember, this is all the information we're going to need here, right? So if we go back and say, can we write on this? I think this is the highlighter. Undo. Here's a highlighter. Where's our purple? That's the pink. All right, that's, I don't know what color that is. Lavender. And then down here we need some red. Right? This is all the values we're looking for. Is that true? Okay, you guys okay with that? But what did we forget to do though? Before we go there? I would say, let's go back. How do we get out of this draw stuff? How about this? Here's my data values. What should we have done really first? We want to look at a chart. We want to scatter the data. Right? So we should have scattered that data first. I was just so eager to get started. Oh. So we should have scattered this data before we got through all these values, because what if our data was so random it doesn't even look like it lines up in a line? So let's insert a what? Chart. Scatter. There's our scatter plot. So let's actually put it up here just to kind of look at it for now. Okay, does that look like our data can actually be fit with a line? You guys see what I'm saying? So that's our scatter plot. That's our data. So, we should have done that first before we did any work, because what if it was random? So you guys want to do the scatter plot. And now that it looks like we can fit that data with a line here, let's see if we could get rid of the scatter plot, or let's move it. Let's make use of this. In fact, if you guys remember, last time, I think I said I can actually find here, this is going to be R. So I need a linear correlation coefficient. That's going to be a lowercase. Remember what I did here? What was the function? Correl, this function. So I put my x values first. Right? Now I go to the second array, put the y values. So what do we get for an r value here? That's actually, r is approximately 0.999. That's almost 1. So remember what we said the other day. If we get rid of the keyboard, it's positive, so this correlation has a positive slope, right? It's a positive R value. It's almost a perfect linear correlation. Remember, if it's exactly 1, it's a perfect positive linear correlation. If it's exactly -1, it's perfect negative linear correlation. So this is going to be probably a linear correlation here. So here's my R value. So if you said to me, Mr. Judge, what would I do now here with this? Well, I'm going to kind of cheat here. And I don't like that it automatically gives you a cap, but okay. Here's my test statistic. I'm going to see if I can enter this in Excel to find the test statistic value, right? But remember, what didn't we do here? Before I go there, let's go back to notes. Let's go back. I'm going to look for a blank spot here, okay? We already did this. So let me do it down here. See if you guys can understand my point. Alpha here was what? Alpha is going to be 5%. Okay? Remember this? We do not what? Reject the null. Here we what? You reject the null. So here, we reject the null. We need our critical values, don't we? So, do you guys remember, what was the sample size? How many data values were here? 1, 2, 3, 4, 5. Okay, 5 data values. Okay. So, if I have 5 data values, degree of freedom is 5 minus 2, that's going to be what again? Is that 3? Okay, so this looks to me, if you want to double check, we have the exact same what? Critical values as the prior example. Meaning, we're going to have what here? Negative 3 point, or that's positive 3.182. Negative 3.182. Because we have the same degree of freedom, same alpha. Okay, and then I'm going to erase this portion here. So let's pretend we never did that. So here's what I want to say. Our R value here was approximately 0.999. Is that true? You guys okay with that one? We need the test statistic. So I'm going to use Microsoft Excel to compute the test statistic here. So I'm starting to enter the formula here. So that numerator was point what? 999. Now let's divide. Remember, what do we divide by? We're going to divide by, for the R, we got the square root key. So you guys could use your calculators. But I'm going to use how Excel can actually do this, okay? Unless you guys want to do it, let's do this here. Parentheses, and then another parentheses here. Is that true? How many parentheses am I going to have? Ooh, I'm going to have, maybe it's better that we use, let's go back. Maybe it's better we use the calculator. Let's use the calculator here. 0.999. There should be a decimal there. Point. How come? Huh?
0.
Thank you. I guess it wants that 0 in front. That's weird. Isn't that weird? These are so finicky. Have to have a 0 before you put the decimal point? Thank you so much. How'd you know that, by the way?
Some of the calculators are like that too.
Online? I've been looking for a good calculator for you guys. Last 2 weeks, I can't find a very good calculator for the iPad.
Well, I'm just used to putting 0 point anyways.
Yeah.
So that's why, like, yeah.
Well, it shouldn't work that way, but all right, divided by the square root. Now let's see if this has a pretty good square root key. Here's the square root key. Okay, the square root of what now? Remember this? It's 1 minus r squared. So 1 minus 0.999. Raise that to what power? Second power. You guys okay with that?
Forgot the decimal.
Yeah, and what's going to happen, though, is it looks like this you're going to have to put a parentheses.
Yeah.
Come on. Square root. And we should be under the radical now. No. No. Parentheses. Good. I guess I have to do it that way. All right. Parentheses of what? 1 minus 0.99. 0.999. That is so irritating. Second power. Close that. Divided by another set of parentheses. You guys see that there? And what's in the denominator for our test statistic? Isn't that n minus 2?
Yeah.
Well, that should be 5 minus 2, right?
Yes.
Okay, you okay with that? Close that. Now double check. See if we entered everything okay. 0.999 divided by what? 1 minus r squared, that's 0.999 squared divided by 3. Is that what we get for a test statistic? 38.701? What do you guys think? Is that what we get? Double check. Did you guys get this in your calculator too?
Yes.
Check that in your calculator. You get 38.701. 38.701. Double check that for me, please. Good. Look at this. This is what we're getting here. So, where is that 38.701 in our decision rule? Boy, it's way over here. It's really past what? 3.182. That's the test statistic value. That's in the reject the null. So we really, you know what this kind of means if it's far? We really reject the null. All right, you guys, it kind of means that. You not only reject the null, you really reject the null. So you're gone null. And you say, what does that really mean? That there is a linear correlation. Now, it's actually a very strong linear correlation because that R value is about almost as close to 1 as you can kind of get in a way. So this is a strong linear correlation. So because it has a linear correlation, go back to Microsoft Excel. Go back over here. We have to find the best fit line now. Okay, you with me on that? Now we're going to find that best fit line. But I want to point out to you, since I already know that it's there, let's see if we can find this here. No, I don't want that. I want to... For the chart. Is it insert? Not draw. Formulas, no. Okay, go to chart. Now there's a way to find that line here. I think it's add elements here. Trend line. Linear. Ladies and gentlemen, this here is the best fit line, so you know. I'm going to draw on this now so it stands out. That's the best fit line. We just have to find that equation of the line. So take a look. Doesn't that look like the data's on that line? The data's on this line, ladies and gentlemen. Okay, just want to remind you guys, that's the line we're talking about. So I just need the equation. It's going to look like this. It's going to be, doesn't matter what color. Y equals, we need to find the M value and the B value. So let's try this out here. Let's find the M value and the B value. You might say, what do I need for M? Well, we need some space here, by the way. Okay, so I'm going to find a blank space.
There's a whole blank already.
Yeah, there is. Good. Let's find the M and B. Thank you. All right, let's write this all down here. Start with your formula here. M is, what's M again? Remember, N is what? Sum xy minus what? Sum x, sum y, over n, sum x squared, minus what? Sum x in parentheses squared. So I need all of those values here. remember, what was n anyway? Do you guys remember? Should we summarize all this here? Let's do this here. N was 5, is that right? I need some xy, I need some x, and I need some y. Those are the first 3 column values. So, go back to Microsoft Excel. 48.02. You guys want to remember this for me here? Do this. We were using purple. Some xy. We need, that's 48.02. Is that right? And then, could you guys remember this for me? And then you say, what else do we need? Some x. And that's what, 4.9? We need some y. Oh, it's 9.8. Okay? Those are the 3 values we need. So 48.02.
No, lower, Mr. Judge. You're covering it with the scatter plot.
Oh, thank you. Ooh. Ooh. Very wrong. Yeah, I'm kind of not a big fan of this. Let's get out of this mode. Okay. Oh, my God. Thank you. Woo. Okay, I want somebody to write down for me. Write down some xy. Okay, it's 458.47. Write down some x. It's 36. Write down some y. It's what? 58.4. Now, write down some x squared. Write this one down. And what's the value there? 306. Did I see it? 0.4. Okay. That value. And then you got some y squared. Write down 712.98. So I want you guys to write all these values down here, okay? You guys see what I'm saying? Let's erase this so we get it out. It's bad karma. Okay, do you guys have all those values? Because you're going to have to read them out back to me. Okay, you have them. You guys okay? Yeah. All right, so what's some xy now? 0.47? What's some x? Is it 36? Okay, what's some y? 58.4? Okay, good. Now I need some x squared again. And what's some x squared? 306.04? What's some y squared? 712 point what? 98. All right, I think we just need these. Is that right? Okay. So we're going to plug all these values in. So as you guys know, n is 5 here. Some xy, 458.47. Some x, 36. Some y, 58.4. N is 5. Some x squared is 306 point what? 04. And then what was some x again? 36. But don't forget we have to square that value. Okay? So how this looks again now, down here, we have m will be 5 times 458.47 minus 36 times 58.4 divided by 5 times 306.04 minus 36 squared. Okay, you guys are good with that? They're all written down for us? Because you're going to have to read this back to me. We're going to compute the slope. Read it back to me as I enter this in the calculator now. All right, so do you guys have that written down? Okay. All right, I have a numerator here. Now, Tammy, what's the first number?
5.
5 times 5.
458.47.
458.47. Good. Minus
36.
36 times what? 58.4, you guys okay with that? Close this. Divided by, what do I divide by? 5 times 306.04 minus 36 squared. Close that. What do you guys get? 0.8111. 0.8111. I'm sorry. Is that 0.811? We're going to go out to three values. Here's my slope value. What you need now is to get the what? We need, what else do we need now? We need the Y-intercept. So let's write this down here. Let's write down the formula. What do we say that was? Do you guys want to use the shortcut formula?
Sure.
Absolutely. Let's put that in red. How's that one? I like the shortcut. Your book didn't give that to you, so you can thank me personally.
Thank you.
Some y minus m some x over what? Over n. Okay, you guys okay with that one? So let's go back up here and find out where's our sum y value. Oh, it's right here. It's 58 point what? So we're going to plug in here 58.4, and then what's my slope value? We already found that one. Slope here is going to be 0.811. I need my sum x value, and that's nice, and that's 36 here. What's the sample size? Is that 5? Okay. So this b value here, 58.4 minus, let's write it down here. Okay, do we have all those values that we needed? 58.4 minus 0.811 times 36 divided by 5. So make sure you guys have that written down so we can punch this in our calculator and find our y-intercept. Okay, what do I punch in? Parentheses, 58.4 minus what? 0.811 times 36. Close that. Divided by?
Forgot to put the point.
What did I forget?
The point, also point.
Oh, yeah. Minus 0.811. See that? It does not. My brain does not want to put the 0. All right, iPad, if you insist, I got to put, or whatever calculator this is, 0.811 times what? 36. Close that. Divided by 5. Good. What do we get? That's 5.8408, which is to 3 decimal places, right? The thousandths. Isn't that 5.841? 5.841. Let's write that down. All right. So, ladies and gentlemen, let's write this final answer down here. I'm going to put that in red here. That line is 0.811x plus 5.841. This is the best fit line, also known as the regression line. Okay, best fit, regression line, that's what this is. So, did you guys write this down? Because I'm about to go back to that page here. 0.811x plus 0.5841. Okay, let's write this down here. But before we do, let's erase this. Y equals, what did it equal? Plus what value? What is it?
5.841.
Now notice this, it's a positive slope, isn't it? Right? It's a positive slope, so that makes sense. It's almost a near perfect linear correlation. So we could very much use this to predict, and we'll be very accurate. So given any x value, we can get the corresponding y value here. And that's how you go about, doing some of this. What do you guys think? Yes?
How come we didn't do the hypothesis?
Well, we did actually. We
Was it
did.
the same problem?
Well, we did. Remember this here? We went back here. We wrote it down here. See this right here? We wrote it under it. It happened to have the same exact setup. It happened to have, since it was the same sample size,
Oh, okay. So
same alpha, 5%. So it had the exact same critical values here. Here's my CV. Here's my CV here. If you guys remember that.
Okay. Never mind.
And the test statistic we found was what? 38.701. That's really much in the reject the null region.
So you said you're gonna give us the graph.
Yeah, I'm gonna give you this table here.
So, but also we're gonna have the graph, right? You said we're gonna have like
Well,
the point.
yeah, I'm gonna give you that. So in other words, what you guys seen on that worksheet, that's what I'm gonna give you.
So in a way, like we would kind of know if it's linear correlation or not before we even start plotting.
If you look at the questions ahead of time, I guess you would know. Because you're saying, oh, I see the chart, I see the graph. Okay. You should kind of know it. Let's go all the way over here. Here's what I'm saying. Remember, you always start the situation by drawing a scatter plot, okay? So if I go back to 1, see this here? Problem 1, study time and grade. So the bivariate sample data below is study times in minutes and the grades in percent earned on an exam for randomly selected grades. Use the 5% level of significance to test the claim that there is a linear correlation between the time studied and the grade earned on an exam. So already, what I did here for you guys in some of these questions, 1 through 8 here, I already created what for you guys? I created that hypothesis test, right? So you have the setup. This is your standard setup. Notice though, I gave you the alpha, 5%, which is why this is 2.5 and this is 2.5. And how many data values are here? Double check. What is n?
6. So it's T2.
There are 6 data values. What's your degree of freedom? We went through that, remember? I understand degree of freedom is here for linear correlation. I understand the confusion. It's a different degree of freedom, right? It's going to be n minus 2 here. So if your sample size here is 6, right? We notice here n was 6. Notice what I put for the degree of freedom here. That's 4. So for linear correlation, it's n minus 2. So I understand when you guys see that, you go, wait a minute, for the others, it was n minus 1. You're right. It was, and it is. It's still n minus 1 for the others. But for this, it's n minus what? 2. All right, so let's be very clear. I understand that confusion.
And that's how you get the critical values.
Yeah, and so you say, well, how do we get those critical values, right? This value and this value. Remember from your t-table? What do you do for the t-table now? For the t-table, let's write that down. You use alpha is 5%, which is that 0.05, and that is 2 what? Tails. The degree of freedom here, the row is row 4. Because 6 minus 2 is 4. So you got the column in your row, and this will give you your what? Your critical values. All right, you guys okay with that? Now, I wrote this down here as kind of a problem here for you, and this is a study time versus grade, but I wonder, what would you do first, though? You want to look at the scatter plot. Because why go through a hypothesis test if it doesn't look like there's any sort of linear correlation? You wouldn't go through it. Okay, you understand what I'm saying? You'd say, wait a minute, you got some random data. What does this data look like? So plot the data on a scatter plot. Now, I just so happened, which was this, a study time example? I just so happen to have some of this set up already. So here's what I want to do here. I'm going to say, okay, I'm going to select this data, and I'm going to do what here? I'm going to insert a chart, and it's going to be a scatter chart. Here it is. Now, I'm going to put it over all this here first. So let me be careful here. There we go. It's a lot better. I'll put it, you know what I'll do? Let's put it over here. How's that? There we go. That's a lot better. Is that big enough for you guys to see? So, do you guys think, does this data look like it can actually be fitted with a line?
Yeah.
Does that data look like? So it looks like we might want to be curious about to investigate whether there's a linear correlation here. We might be able to see that. What do you guys think? All right, you guys understand what I'm saying? So you might say, okay, there might be a linear correlation. Well, how do we know? Go back to your what? Go back to your hypothesis test. Compute your what? Compute this value for R. And then compute your test statistic. Okay, you okay with that? So now that we know that the scatter plot does look like our data, our bivariate data is in the form of a line, can be fitted by a line, let's actually do that. I'm going to cheat again because I like cheating. Well, I don't, but you guys understand my point. R. And let's do that little r, okay? Now, you guys remember, I already know the function for that. That's called correlation. Check to the correl. And then I need the first array. This is the x values, and this is my y values, the second array. What's this value? What's that approximately? Anybody want to read that off to me? That's about 0.950. That's about 0.950. So I already know this value. 0.950 for my R value. Should we change the color? Does that look like, should red go with that, or should we change that color? Kind of partial to blue. All right, R is about 0.950. So what do we need? We need the test statistic. We need this now. Is that true? So how do we get the test statistic again? Let me do this out. Here's our R value. We already know R is going to be what here? 0.950. Now, the test statistic, out here, we plug in 0.950, 0.950, and here, what was N? Is that 6? So my test statistic is 0.950 divided by square root 1 minus 0.950 squared over, I could put 6 minus 2, but can we put 4? Is that 4? You guys understand what I'm saying? I'm going to put 4 here. Okay. Calculator. 0.950. See, I can learn eventually. Divided by square root function. Parentheses. 1 minus 0.950. And you don't even have to put that 0. Close the parentheses. Divided by, what is 6 minus 2? Was that what we had to do? Double check.
Yeah.
What do you guys think? Is that okay? go out to the nearest thousandths. 6.085. Here's my test statistic value. 6.085. So you might say 6.085. Where's that on my decision rule? It's out here. Is that right? 6.085 is bigger than 2.776. What neighborhood are we in? Anybody want to tell me what neighborhood this is?
Reject.
Yeah, we're going to reject the what? The null. We're in here. We're going to reject the null. Goodbye, null. What does this actually mean? You do have a linear correlation. So now that we know that there's a linear correlation, what do we do now here, ladies and gentlemen? Yeah, we're going to have to find the regression line or the best fit line. So we do have a linear correlation here. Okay, you guys okay with that? Now, I'm going to use some spacer to find that. So let's remember, all these values we didn't even get. So let's summarize here, okay? We need n. N is 6. We need some xy. We need some x. We need some y. Is that true? And then we also need some x squared. And we need some y squared. So we need all of these values here. So let's go back to the original spreadsheet here. And we need to fill in these columns, don't we? Move this out of the way. So let's fill in these columns. So again, darn it, let's see what we can do here. Equals, oh, it's the wrong place, here. Equals, take the x value, raise that to the second power. And I wonder if I can, what do I say fill here? Not fill, let me double check here. Yes. Oh my God, it is there. Oh, I found it. So it's just the first time I ever used this program. First time I ever used this program. Good. This is going to save us some time. Okay. Equals. But be careful. I did this a little differently, so be careful here. See if you guys can figure that part out. Raise to the second power. Okay. And we're going to do what here again? Fill. That's autofilled. All right. Now what do we do? Equals x times y. And then we're going to fill that. And that's really autofill. So I don't know why Microsoft just didn't put autofill if that's what it is. God, that bothers me. Sorry about that. I get to sound like an old man. Inconsistency really is an issue. Now, what do we do with all these? We have to add, right? Sum. We're adding, summation. Sum. Yes, we're adding those. Summation. Yes, we're adding those. Summation. Nope, we're adding these. Summation. Nope, we're adding these. Summation. Nope, we're adding the column, not the row. Okay, you guys see that there? All right, you guys see that there? Maybe that's a little better for you guys. Okay, so again, we're going to need each one of these here. Let's find our highlighter. Let's do blue. X, we need the sum x. Y, we need the sum y. X squared, we need sum x squared. Y squared, sum y squared. XY, we need the sum what? Okay, we need these here. Is that right? Does that cover this up now up so you can't see? Probably. Let's do that again. I guess that's why they have the nice pastel colors. Let's do a blue. X, here's our sum x. Y, sum y. X squared, sum x squared. Here's a y squared column, here's sum y squared. XY, sum xy. So let's write that down. Sum x, sum y, sum x squared, sum y squared, sum xy. And in fact, what's n again? N is 6. So in fact, if you guys wanted, we can actually write it all here on this page. Should we try that out, or you want to go back to? Make sure you guys copy this down, okay? You guys have this all down here? All right. Okay, what was sum xy? What is it? 275 point?
No, 27520.
27520.
Yes.
Is that 0.20?
No.
Okay, 27,520.
Yes.
Okay, what's sum x?
350.
What's sum y?
418.
What's sum x squared?
24,500.
What is it?
24,500.
24,500. Okay, what's that sum y squared?
31,790.
31,790.
Yes.
Anybody second these values?
I second these values.
Thank you so much. It was second. All right, now we need the slope. Is that right? Our slope formula. M is n sum xy minus sum x sum y over n sum x squared minus sum x. Okay, you guys okay with that? Isn't that our slope formula? Okay, so let's plug these things in. I'm going to change colors. And here, what was n again? N is 6. Good. Sum xy, 27,520. Sum x, you guys told me was 350. Sum y is 418. 350. Don't forget to do what here? Square that. So, we have 6 times 27,520 minus 350 times 418 over. Ooh, we forgot sum x squared. What's sum x squared? 24,500. Okay. 24,500 minus 350 squared. Make sure you guys write this down because you're going to have to read it back to me. Right? And double check to see whether we have these things here correctly here. All right, let's find out. All right, let's find out. What do we enter first? Is that 6? 6 times what number? 27,520 minus. Is it 300 and what? 50 times 418. Close that. Divided by, that's weird. Divided by what? 6 times, what's the next number? 24,500 minus 350. Is that to the second power? Okay, close that. What do you guys get? This is 0.768. It's 0.768. All right, you guys okay with that one? So my slope here is 0.768. That's my slope. Now, how do we get the y-intercept again? What's that b going to be here? Remember this? So we put it in red. Sum y minus m times what? Sum x over n. Is that true? All right, you guys remember that for our y-intercept value. So sum y here is 418. My m is 0.768. The sum x value is 350. And maybe we want to put that in blue, I guess. Okay. Sum y, oops, 418, is that right? M, 0.768. Sum x here is 350. And what's our sample size again? Is 6. So here's my b. 418 minus 0.768 times 350 over 6. Let's find out what this b value is going to be. So make sure you guys have that in your notes written down, because again, I'm going to have to ask you guys what the value is. Okay. 6 times what number? Well, not 6. What's the sum y? Do you guys want to tell me? What was that sum y value?
418.
418 minus 0. What was that? 7? 68. Good. Times 350. Is that the sum x value? Close that. Divided by 6. Did I forget something?
The 6 at the beginning of, this is for the b value, right? Oh, no, I'm sorry.
Nope, we don't need a 6.
Oh, you're right.
Okay?
And then
Anyway, so what do we get here? 24.86, what? 7. Good. Go to the thousands. 24.867. Do you guys see it? So this is what we're going to have to use here. Let's find our best fit line. So make sure you guys write down the slope, 0.768, and the y-intercept of 24.867. Okay, so go over here. Remember, we're going to insert was it insert? Let's go here. Home, no. Data, no. Draw, no. It's insert. What was it under there again? Charts. I don't think that was it. I think it was line, maybe? Oh, whatever. Ah, nope. Let's go back. No, it is under... Okay. It's not insert.
Like equal correlation or something?
No, it's under chart. Okay. I think it was under chart. Sorry. It's insert elements. It's kind of weird. Trendline Linear. There it is. So notice here, we're going to draw now. What was the equation here? Let's change that color. I kind of don't like that blue. Okay, should we do red or should we do dark blue? Maybe dark blue. What was the slope? Is that 0.768? What's the y-intercept? Was that 24.867? Isn't that weird? I don't know why I remembered it, but I did. Okay, that's the line here. Let's find this line here. See that line? That's the line they're talking about. That's the best fit line, also known as a regression line. So this regression line is what we can use, this equation, to predict now. Okay, can you guys see that line there? Is that okay? You know, and so this is how we go about actually finding these values. We're going to use those formulas here. And so that's pretty good because you can see kind of this data, I guess. Let me do that here. Maybe you can see it a little better. There's a here's a data value, here's a data value, a data value, a data value, data value. Those are our data values. And it looks like we can actually fit that in this line here. That's what we're looking for, best fit line. Now, remember, I'm going to remark here really quick. This R value I got using Microsoft Excel. But last week, if you guys recall, to get this value last week, what did you do? Let's just do that here. We use what formula here? We use this linear correlation formula that's written down, right? So, and here is 6 from last week. Sum xy was 27,520. Sum x here is 350. I'm looking at my data values here. See this n is 6, sum xy, sum x. Now sum y is 400 and what? 18. You okay with that? And then down here we have what? It's 6 again. And then we have sum x squared. This was 24,500. And then I got sum x here again. This in here, this is 350, but I have to raise that to the second power. I do that again over here. This is 6. Sum y squared was 31,790. And then sum y here is 418. Don't forget we raise that to the what? Second power. So I want to remind everybody, as of last week, we had to enter all of this there. And I don't know if there's any space here now. You know, if we want to verify this, you know, but you would enter all this in the calculator the way we did last week. Maybe we'll try to verify this. Can I erase all this here? Should we try that just to verify it? Just to make ourselves a little crazy? Okay, getting rid of our best fit line information. We're going to verify the R value, the linear correlation coefficient. All right, so we used all these values here. So let's see if we can write this down here. R is going to equal 6 times 27,520 minus 350 times 418. Now, be careful here. This is all over 2 radicals, right? 6 times 24,500 minus, maybe it'll fit, 24,500 minus 350 to the second power. Six times 31,790 minus 418 to the what? Second power. This is my linear correlation coefficient. We're going to verify that R is approximately 0.95 what? 0. So make sure you guys write all this down, because what you guys have to do is punch that in your calculator. Okay, so write this stuff down and let's see what we get. Okay, do we have that? Because we're going to try this out on this calculator here, okay? So you're going to have to help me out here. You're going to have to read this back to me so I can enter it. Okay. Parentheses, 6 times, what do I put? 27,520 minus what? 350 times what? Times what? 418. Do I close the parentheses?
Yes.
Okay. Now remember, divided by, open that parentheses. And I don't know what that means here when I put that E. Maybe I hit it too hard. Open that parentheses here. Now we're going to put a square root. And I'm going to go under the radical here. Oops. What's under the radical? 6 times what? 4,000?
24,500.
Okay, minus?
350 the second power.
Good job. You guys okay with this one? Now, what I have to do is get out from this radical. So I'm going to use my arrow key. Then I'm going to multiply. See, I use the arrow key to get out of the radical. And then I have to enter another radical because there was 2. Is that true? You guys okay with that? Now, this is going to be, again, 6 times what?
31,790.
31,790. Is that right? Minus what number?
418 squared.
418 to the second power. Is that right? So I have to get out of this. So I use my arrow key, and then I'm going to close this with the parentheses. Okay, so remember, this is the stuff we worked on last week, computing that linear correlation coefficient, this R value. So double check this calculator, right? You see what I have here? Oh, I like that. You can move it around. Look at that. My numerator divided by, I guess I should have used this last week. What do you guys get for the linear correlation coefficient? What's this value for R? That's point what? 0.950. Is that right? Let's double check. What do we say it should be? 0.95 what? 0. So sure enough, when we did this using Microsoft Excel, it was correct. It's 0.950. Okay, you guys okay with that? All right, now, here we go. Okay, we're going to continue here, right? And let's go through the second problem here. They're talking about customer service and computer sales here. Okay, so the bivariate sample data below are the number of customer service calls per week and the computer sales in thousands of dollars at a computer wholesale store. This problem says use the 1% level of significance to test the claim that there is a linear correlation between the number of calls per week and the computer sales in thousands of dollars here. Okay, so let's go through and remember here. The first thing you really do, in all honesty, is you go back over here. Now I'm going to put this in gray here. What you guys are going to do is you're going to look at your data here. See this?
See nothing.
Ah, you guys see nothing. Okay, I apologize. Here, we got to switch you to VGA. See? Told you. There you go. All right. Okay, now you guys can see. So let's go back and I'll remind you. you're going to look at your data. So the first column, I guess we want to use red maybe so it stands out. That's going to be our what? The x variable. There's the y variable. So I know this is a linear correlation coefficient or linear correlation kind of question, right? And you start with this data here. And this is a customer service and computer sale calls. So here's our data. And what I'll do here is I'm going to go out to my spreadsheet here. Okay. And let's see. Let's make this a size. If we could go back. Okay, let's kind of change that. And so here's the data. Okay, so we have, notice the following here. Let's delete that. Okay, so notice we have actually 6 data values here. So I have this data, and again, I'll leave even some of this chart online for you guys as well, I guess, right? And we have to do a scatter plot because we don't know if the data is actually going to be in line, or we should say can be described by a linear equation. So we want a scatter plot with the data. So here's what we're going to do. I'm going to create a scatter plot, and it's going to be insert, I believe, chart. So I'm going to go down to scatter here. And there we go. So let me demonstrate to you what we're looking at here. So there's your data. And could you guys see those dots there? All right. Let's double check here. So do you think that data can be represented by a line here? A best fit line possibly? Can we represent that data? So yeah, so you create the scatter plot and you go, okay, so I think I can actually, model this by a line, but we don't know for certain. So we're going to have to actually go through again the process of finding if there's a linear correlation. So if there is, we're going to find the best fit line now, and this is what we're going to use that we have already described there. Okay? So we're going to go through that process again, and remember, I'm going to move this really out of the way, because what do I need? What kind of information do I need again to determine that linear correlation, right? So if we go back here, we're going to set up the test. We're going to say alpha here. What's alpha? Right, you see this alpha? Alpha is 5% or 1% in this example. So what I already did for you guys setting up the test is there's your what? 0.05%, 0.05%. Okay, you guys okay with that? And there's your alpha. We need critical values here. So to get these two critical values, remember, what did you guys do? You use the alpha of 1% 2 tails. So I want to remind people here how you did that. So you're going to use alpha being 0.01 2 tails. And this question came up with the last class. What's your degree of freedom for linear correlation? Anybody know the degree of freedom here? For linear correlation, your degree of freedom is actually n minus 2. So there was people who were very confused last night about that, and I believe because they didn't get to this homework yet, because they're still with the degree of freedom being n minus 1. So for everything else that we use in our t-table, the degree of freedom was n minus 1. But for linear correlation, it's n minus 2. Okay, you guys okay with that? Now you might say if there's 6 data values, what's 6 minus 2? That's 4, is that right? So on your t-table, you're going to look for the 1% two-tail column, and then you look for row 4, and what you guys should find there on your t-table is actually these critical values. Okay, you guys okay with that? So I want to remind you guys that's how you actually do this. You find those critical values. So you might want to practice that and make sure it's 4.604 there. And since this is two tails, it's minus 4.604. So we're setting up our hypothesis to test for a linear correlation. Okay, so what you have on the right side here is all of that information for the test. What we have to find now, and I'm going to go down here, is we need these things. We need R, we need the test statistic, and then we need our conclusion. So to compute R, this is how we're going to do it. So as you guys can see again, what we really need to find that linear correlation coefficient is we need the sample size n, and we know it's already 6. Is that right? So let's write that down. We need sum of xy. We need sum x squared. We need sum y squared. We actually need sum x, and we need sum y. So we're going to need every one of these values here to answer the question. Okay, so this is what we're going to do now. So we're going to go back here, and we're going to create here. This is xy, and I guess it likes to start with a capital. X raised to the second power, and we need y raised to the second power. Is that right? Okay. So here's how we're going to find those two values again. Okay, so I'm going to do this. I'm going to enter here equal 10 times that 37. Okay, so that's 370. Now, I'm going to do the following here. I'm going to do what's called autofill. There we go. So what that did for me is it actually multiplied the x and y values for every paired data. And then now I have to find the column x squared, and I do the same. So here we're going to have this value raised to the second power. And yeah, we said that okay. And then I'm going to do autofill. So it squared every one of those values here. Now I'm going to do the same here. But I'm going to take the y values now, 37. Square those. Here's what you get. If you guys know. Oops, we need to do autofill. And these are the values we need. Okay, so we're going to go through this process. We got all those values. And again, you don't have to necessarily write this down, but if you want to, that's fine. I'm going to post this online for you. And now we're going to have to sum these, right? So we're right here with the sum. So we're going to have to sum every one of these columns here. So the first sum, we're going to sum the x column. And so we're going to add now here. Here's the summation. So here's my first sum. I'm going to repeat the process. And when you get here, it looks like it wants to add rows, but we're going to correct that. And then here, oops, no, we want a summation here, sorry. So we're going to add all of these values here. Okay, let's double check here. So these are the sums here that we actually need. Okay, so these are the values that we want to consider here. So let's highlight them, I guess, I don't know. Right, so I want to make sure you guys write those values down, okay? So sum x is 99, sum y is 265, sum xy is 4,554, is that right? And sum x squared is 1783, sum y squared is 11,929. Okay, do you guys have those values? I'm going to need your help with this. So what was the sum xy, so we can write this down? Okay, you guys know, what are the values? What's sum xy?
765.
What was it, 765? Okay. What's sum x squared?
289.
289, good. What's sum y squared?
2025. Wait, sorry. I'll give you the wrong ones. XY is 4554.
Okay, 4554, okay.
X squared is 1783.
Okay, let's
And
write
Y
this.
squared is 11929.
1783. What's sum y squared?
11929.
All right, what's the sum x value?
99.
Okay, and then the sum y value.
265.
All right, good. We're going to use these things here. Okay, we're going to use all these values. Now remember, you say, well, what do? I plug them into this, this equation here, and then we're going to punch it in our calculator, and we're done. So n here is 6. Sum xy, 4,554. Then I have a sum x being 99, so this is 99 here. And then sum y will be 265. And then under the radical here, all this stuff, we have n is 6, sum x squared, 1783, sum x to the second power. Now that's 99. Now don't forget, we're going to have to raise this to the second power under this radical. So I'm going to notate that. Now n here is going to be 6. Sum y squared is going to be 11,929. Sum y is 265. And then don't forget, we have to square that one too. So as you guys know, what I do is I put the numbers next to that, and then I'm going to write it down here. All of this. So we can have 6 times 4554 minus 99 times 265 over 6 times 1783 minus 99 squared. 6 times 11,929 minus 265 squared. And then that's all under our radical. Okay, so make sure you write this down and double check as we go along, because I'm not even awake yet. And we're going to punch this in our calculator. Okay? All right. Okay, just to remind you, make sure that's power 2 here, power 2, okay? All right, let's see if we can punch this in, and let's make sure that 4 is a little better, 4554. Okay, so here's what I'm going to do. I'm using this calculator interface. It's the only one I've found. I've been looking for 2 weeks at least to try to get a good iPad, whatever they call it, program, you know, that you can actually see the calculator, because the other ones you can't, so. All right, let's punch this in. Okay, what was that? 6 times what? What was the next number? Is it 4554? Minus 39. Good. Times. Is it 99? Thank you. 99 times what number?
265.
Okay, good. Close that. Now, we're going to put divided by. Remember, we're dividing by, in the denominator for r, we're dividing by the product of two square roots. So I have to open that parentheses. And now we hit the square root key right here. And I want to make sure now everything I enter is under that radical. So what's under the first radical? Right? 6 again, is that right? 6 times. Remember that r is really the standard deviation for the x variable. So what's some x squared? What do you guys have coming next?
1783.
Okay, 1789 minus
83.
83.
No, 1783.
1783. I'm so sorry. 1783 minus
99 squared.
99. Okay, so we're going to square that here. Okay, you guys okay with that? Now, I'm still under the radical. So how I get out of the radical is I have to use my arrow key. So your calculators probably work the same way. So get out of that radical and now hit times, because I have to multiply it with a second radical. So now I'm going to multiply, I'm going to enter the standard deviation for the y variable, right? So what do we got? What do we get now? I think it's 6 times what?
11929.
Okay, minus,
265 squared.
thank you so much, 265 squared. Now we're going to get out of that radical. Does anybody know why we have to do that? Because I have to close my parentheses here. Because between those two parentheses, after the division sign, we're saying to the calculator, hey, calculator, guess what? Divide by that product. And it's the product of two square roots. So what do you guys get for this value? Let's go out to the nearest thousands here, 3 decimal places. This is 0.989. What is this going to give us? 0.99 what? 0. Good. 0.990. Let's remember that. Okay. So here's what we have as a linear correlation coefficient here. Now, I'm going to go back here, and I'm going to remind you guys, guess what? I'm going to enter here, Microsoft Excel, by the way. It's called correlation, Corel. See this function? Believe it or not, and I'm going to have to enter the first x values here. So there's our x values. Now I have to go to the second array for the y values. Okay. I want you guys to take a look at this here. Isn't that really also what we just did? Isn't that the same value? Is that 0.990? All right, you guys okay with that one? So it looks like we were correct with our computation. So I'm just double checking here for you guys that yes, it's 0.990 approximately. Now let's go back to our hypothesis test and let's see. 0.990, where would that be on our decision rule? Well, it's actually positive, right? So it's to the right. Is it past our critical value? No. So it's actually not. It's almost 1 over here maybe. Here's where that test statistic lives. That's 0.990. What neighborhood are we in? We're in the what? Do not reject the what? The no. Is that true? Do not reject the null. Double check. So 0.990, is that our test statistic? Let's double check everything. So what does it mean if we don't reject the null? Maybe I should change the color here. If you're not rejecting the null, what's the story?
No linear correlation.
There is no linear correlation here. I apologize. Let's wake up. We made a mistake. We made a very big mistake. We're not done. Why aren't we done? I apologize. We're not done. Just trying to see if you guys are awake. This is our R value. What do we need to do with the R value? Good, thank you. 0.990. 0.990. What's n again? N is 6. So here's our test statistic. It's 0.990 over square root 1 minus 0.990 squared over 6 minus 2. So we have to compute the test statistic, that R value. Very bad, very wrong. We got to really wake up. I thought I had a good night's sleep. Okay, we're going to punch this in the calculator. So here we go. And by the way, this particular calculator, you have to put 0 before this. And you don't have to put the last 0, but I will. Divided by, and you have the square root key. Remember this? And I have to put a parentheses, because I have to tell the calculator, hey, calculator, under my radical, I have a numerator. 1 minus point, again, 0.99 up, and that's not 1. 1 minus 0.990, raised to the second power. I close that parentheses, and I divide under the radical. I can put another parentheses, if you guys have to, and say 6 minus 2. Okay? And close that, or I could just put 3. 4, yeah, 6 minus 4, absolutely. Thank you. See, I need enough. Today's a bad day to record. 6 minus 2 is 4. So what's the test statistic? And this is kind of weird for me. That's why I should wake up with this. What's this approximately to the nearest thousandths? Isn't it 14.036? Okay, test statistic. 14.03 what? 6. There. Now this is a lot. Now this is a lot better. Now here's why this is a lot better, right? Where does this 14 live in your decision rule? Now this 14 is really what? Beyond our critical value here of 4.604. In fact, it's like way over here. This is our test statistic. 14.0, what is that, 36? Yeah. And here's the thing about that. What neighborhood is this actually in, right? This is really in what? Let's paint this. This is in the reject the null neighborhood. So when we reject the null, we say, okay, null, you're gone. The null is now rejected. It's gone. So what's the conclusion going to be here? See this here? There is a linear correlation. Now, let's put the values here so that we can summarize correctly. R we got was 0.990. The test statistic is 14.036. Your conclusion is simply that the claim that there is a linear correlation, the data suggests that yes, there is a what? Linear correlation. When your value for R is close to 1, or it's close to -1, that's a tip-off that that's actually a linear correlation, so you guys know. There's a way we can do this using our level of significance. I haven't, like I said, it's in your notes. I'm not going to videotape that. I'm going to only go with one method because I find that's good for people to do one method over and over again until they get their skill sets sharp. And then you could actually talk about other kind of approaches and methods. But to let you guys know, this is why I was using that. I made that kind of mistake. I'm thinking, okay, I'm going to compare this with alpha, but no. We're doing the classical approach. So the classical approach here, by setting up a hypothesis, we need the test statistic. And that actually reinforces everything else that you guys studied with hypothesis testing. So that's why I do it, because it reinforces everything, even using a t-table. So it's a reinforcement. That's why I've done this. So yes, our conclusion is definitely that there is a what? A linear correlation. And we know from the chart that it looks like there was a linear correlation. Okay, so you guys okay with that? Yes.
Can you see again how you put the test statistic in the calculator?
Oh, how do we do that? Take a look here. Yeah, it's all right there. So make sure that that computation is in your, that you can actually handle that. That we don't have to put divided by 6 minus 2 in parentheses. We could just say 4 divided by 4.
Because I'm getting different.
It might just be there's an error with what you're doing. Okay? We could double check all that later. Because really, this is what we did what? Last time. Is that true? We did these things last time. So what is it that you do now when you find that there is a linear correlation? So go back here. Remember this? Here's what we're here to study today. Now I'm going to find this here. I believe we have the chart. I'm not sure where it is. This is only like the second time I ever used this. So maybe it's down here. Okay, we're going to find, no. Recommended? I don't think it's recommended. Charts. Is it add-ins? No. Let's draw. No. It's not a formula. Okay. I think it's view. Chart. Elements. There it is. Add an element to our chart. That's what we do. We go to the chart. Now here's what I'm saying. Trendline linear. So can you guys see this here? In case you guys can't see this. This is what I want to point out. Maybe you can see it a bit better. Your data looks like it strongly correlates, meaning if you can see the data values, I know I covered up some of the data values there, and I'm just emphasizing this best fit line. So what we just showed was that there is pretty much a strong linear correlation here, very strong. So we can model with a linear equation, a best fit line, a regression line also known as. So we're going to find that regression line. So the next step here is to find the regression line, and you might say, well, how do I do that? Well, you guys see your formula for your slope? That's what we're going to do. But this is what we're trying to find now. The question is, what's this equation, right? Remember, this equation is going to be of the form y equals what? mx plus b. So yeah, that data strongly correlates to a linear equation. So let's find this out now. And what I'm going to do now here is a couple of things. We can erase this, or we can use this. Let's actually use it here. How do I get our slope again? Do you guys remember? It's on the board again. N is sum xy. Okay, maybe I'm going to erase this. Okay. Just got to get out our big eraser. Okay, so m for our slope will be n sum xy minus sum x sum y over n sum x squared minus, remember this, sum x in parentheses squared. This is how we're going to get our slope. Yes?
Do you mind if we use what the book describes it as, like y hat, b0?
Yeah, that's fine. That's fine. That's fine. Yeah, it's very fine. I'm just trying to show people from first principles what that is. Remember? Yeah, you could use you could use that. That's very good. Let's plug these things in, right? What's the value of n here again? That's 6. What's the value of xy? 4,554. What's sum x? 99. What's sum y? 265. 6. What's sum x squared? 1783. Sum x again was 99, but don't forget, you're going to have to do what here? Square that number. Now, this is going to give me my slope. We're going to approximate this to the nearest thousandths again, and that's going to go in our denominator, ladies and gentlemen. All right, that's going to go in that denominator here. Notice there's no square root here. So this is going to give me my slope here. Okay. So tell me, what do? I have to start with the parentheses here. And I know I have 6 times, and you guys, we got to get you back here. Okay. What do I put? Sum xy. What's that value?
45, 55,
Okay. Minus, what's sum x
99,
and sum y?
265.
Close that parentheses. Divided by, now I'm going to open another parentheses because I have a whole expression down there, right? I'm going to have that 6 times. Now, I need sum x squared. What's that sum x squared?
1783.
Thank you so much. Minus the sum x to the second power. What's sum x?
99.
Thank you. Close that parentheses here, ladies and gentlemen. Double check that we entered everything okay. And it looks like our slope is about 1.214 to the nearest thousandths. Now notice it's positive. So that means our slope is uphill, right? Positive 1.214. So, all right, m is 1.214 here for you. Okay, we're on our way. There's our slope. Now, remember, I'm giving you a different version in your book. And I guess here I colored it green on the board, so we're going to use ELAC green. So our y-intercept's now going to be sum y minus m times, and if I put it down here lower, sum y minus m sum x over n. Now, I think that version is a lot easier to use than the version that the book wants you to use. You guys agree with that one? And in fact, we even have another easier version, but, you know, B is going to be that, you know, it's covered by the screen, but you have the mean of y minus m times the mean of x. Anyway, we could use that too. But I like this because we already have this information on the left here. This is why I like that. So I know sum y is 265. Is that right? You guys see it right here? This is what I'm talking about. We have all that information available for us to use. And m, we know, is what we just got, which is 1.214. Sum x, you say, where's my sum x at? Well, it's right here, and it's 99. So we're going to put 99 there, and then what is n here? N is 6. So b here is 265 minus 1.214 times 99, everything over 6. We're going to have to find what that y-intercept value is. 265 minus 1.214 times 99 over 6. So make sure that's in your notes because you guys are going to have to help me out here. Okay, let's clear this. What's in our numerator here? Right, what do you guys have? What's the sum y value? Huh?
265.
Thank you. 265, and then it's going to be what? Minus 1.214. Good. Times 99. Good. Close that, and we're going to divide by what's n? 6. Double check to see if you guys have that there. All right, so double check there, and you get now 24.13 what? 6. Okay, 24.136. All right, 24.136. So let you guys know here, I'm going to write it here this way. That best fit line is 1.214x plus 24.136. This here, ladies and gentlemen, is what you find and use to predict for this physical situation, right? The relationship between the two variables x and y is in fact linear, okay? And and again, you might say, well, what does my book use for this formula? Do you guys know what that book uses? What symbol does it put in front of that y? Does it put it's not a mean symbol, what is it? It's like a caret sign. So that's your linear, that's your best fit line. That's also known as your regression line. So it's up to you. I'm fine with you just putting it as is, you know, from beginning algebra. Okay, so this is your regression line. So if we go back here, you said, well, what was this to begin with? Well, that regression line is 1.214 times x plus 24 point, what was that value? 24 point what? 136? Okay, we'll get rid of this. And this is actually what you're looking for. This is only when there is in fact a linear correlation, but you first start by drawing your scatter plot, putting that on your XY axis. Okay, you guys okay with that? That's the full process. And like I said, you might say to me, okay, Mr. Judge, then how do you use this? Well, remember, if x is 18 here, if I plug in 18 for x, could you guys tell me what y becomes? Because I can tell you 18 is maybe somewhere over here, right? So we can use this to predict. It should be somewhere over here so you guys can see that. Right? This is why we actually go through the whole thing. So you just have to multiply 1.214 with 18. And then you have to add 24.136. So maybe I'll use this other computer and do it myself, or I can ask you guys to do it. What do you guys get here with this? You guys know? Okay, I'll do it myself. 1.214 times, we said 18? Okay, plus 24.136. What do you guys get? Anybody want to get an answer?
45.99.
Yeah, 45.9 what? I got 988. And if we want to approximate to the whole number, it's about 46. And that looks like it makes some sense here. If you guys can see that here. See that here's 50. There's where 46 would be. So we could actually predict. So, I mean, x represented, right? When it's 18, we get 46. So x represents, again, what? If we make 18 calls per week, we can bank on $46,000. Right? You guys okay with that? 18 calls gives us how much? $46,000. We're predictive now. Yeah.
Where did we get the 18?
I just made it up. I just want to show you why you care about that line. Yeah. I said, okay, because on your study guide, don't you guys have that there too? They ask you to be predictive. Yes?
I was gonna ask you for the study guide, you gave us the y instead of the x.
No, we'll take a look at that, but we'll give us you the. Oh, okay. I'll take a look at that just in case. Thank you. Are you done, by the way, with that? We talked about that earlier. Thank you, because there's other students who are done too. Use that for Thanksgiving time. Good for you. That's how you do that. Okay, let's try another one. Okay, you guys. There you go. Let's go for the next one. What do you guys think? I don't know if I want to go through all the detail, but this one's kind of fun. Police officers and muggings. The bivariate sample data below is a sample of the number of police officers on patrol in a small city and the number of muggings in the same size city. And this is a typo, note to self, we have to use the 5%. So, let's write this down. Ooh. Actually, you guys don't know, I actually changed this. So that's why there's a typo. So, use the 5% level of significance, and I want that to be actually blue. You're going to use the 5% level of significance. Okay, 5% level of significance, you might say, is what your book uses now for Triella in this section. He transitioned. Other books use 1, 5, 10%. Okay, in the past you use 1, 5, 10%. Anyway, test the claim that there is a linear correlation between the number of police officers on patrol and the number of muggings. I'm just kind of curious, what do you guys think should happen? If you increase the number of police officers on patrol, what do you think happens? The muggings increase or decrease? The increase in muggings? I don't know. Let's look at the data. Guess that's why we gather data. Let's take a look. Police officers and muggings. There we go. So, could you guys see that there? Should I make it bigger? Because the last time it was so big, we couldn't see everything collectively. So, anyway, here's what I want to do. I'm going to create a what? A scatter plot. Is that right? So, we're going to create a scatter plot. And I'm going to insert a chart. Scatter. Okay, here's kind of the data. Now, I don't know about you guys. How does that look? That looks a bit what? Does that look like we can fit that data with the best fit line? I don't know. It's kind of questionable. It does look like there is some correlation that's negative because of the fact that the line that we can create looks like it'd have a negative slope. So that way we look at this and go, it can have a negative linear correlation. Now, being negative just means the slope of the line is negative. It just means decreasing. So it goes back to my original question here. It looks like if there is, we don't know yet, we have to test this. If there is a linear correlation, it may be that the greater the number of what? I think it's kind of backwards, but is it backwards? Let's see. Well, I guess they're describing muggings, but the X variable is the number of police officers, okay? So what's going on here is as X gets bigger, the number of police officers, Y gets smaller. Does that make sense? Now stop and think. If you add more police on patrol, does that decrease crime? You guys know what I'm talking about? This is some data. We took a sample of data. And the crime they're talking about here is in particular muggings. So, I mean, what I said was not very good in terms of a linear correlation, but it's giving you guys the idea. I'm particular because there's a lot of different types of crime. But we're seeing, do muggings, what's the effect? All right, you guys okay with that? That particular crime of being mugged. What's mugging? Do you guys even know? Is that a term that people use these days? Or do the people use a different term for... What's a mugging? Do you guys know? You got robbed, right? Okay. So what do you think? If there's more police presence, will the chance of you being robbed on that street decrease? Maybe, maybe not. This is the data. Let's see if there's a linear correlation. Okay, so we drew the scatter plot. Now, it looks like there's a couple of data values that could be outliers you might want to consider here. So I just want to throw that out. And outliers for linear correlation, it really affects this deeply. Okay, so linear correlation is highly affected by outliers. So at times you might have a data value that you are allowed to, get rid of because it could be an outlier, and you can kind of get a better best fit line there. So I can see one data value that's a little troubling, but we'll double check here. Okay, so I want to do a couple of things here. Well, let's do it all together here. You guys okay with that? So I'm going to move this out of the way. And by now, you guys know, what do I do here? I'm going to have to enter what? This is going to be XY. We've been doing it that way. This is X to the what? And again, it's always capital, so. Come on. X raised to the second power, and then we have a what? Y raised to the what? Second power. Okay. So here, we're going to have to enter all this data again here. We get equal 20, times 8. Is that right? Return. I'm going to do this a little different today, or in this example. I'm going to say equal, here's the x variable, and I raise that to the second power. Is that right? And then here's the y variable, and I raise that to the what? Second power. Okay. And what am I going to do for the rest? You guys remember? We're going to do that autofill. So that's going to streamline the process of the arithmetic. And we're going to do the same thing here. All right, and then I'm going to take this one here. There we go. We need the sums. Is that right? So to get the sums now, we're going to use our summation. And generally that first one is always good. It's the third one that isn't. Sum. Watch, it's going to try to add a column here. And I'll hit sum. I'm sorry, row. We need to add the column. So it adds the row. And sum. And sum. Okay. Let me go back here because that doesn't look good. Okay, we're going to go in here. Summation of, make sure it's the real value because you can't see with this here. Okay. I'm going to get rid of that. There, we can see everything a lot better now. So, remember, the whole idea here is for you guys to do what? Is that too dark where you guys can't see that? Should we lighten that up? Okay, I want you guys to get these values here, right? I want you to notate that n is 8, isn't it? N is 8. And I want you to get the rest here. Determine sum x, sum y. Copy that stuff down because we're going to use it. Sum xy, sum x squared, sum y squared. So I'll give you guys a few seconds to get that. And then maybe as you do that, I'm going to increase the size here since it looks like we can. Okay. Let's make this here. There we go. Looks a little nicer. So before, I'm going to try something here. Okay, before we actually go through the process, remember, I'm going to hit what here? I'm going to put my correlation function. So when it says array 1, that's just the list of data. That's the x values. Okay. Now I hit the second array, which is the y values. Okay. So it looks like there's a negative linear correlation of negative what? 0.782. Just so you guys know, we're going to verify that, right? Okay. Okay, you guys get these here? So let's kind of remark. Let's highlight that. I think we use the gold or whatever this is. Okay, we know this value R. Let's do, yes?
So what did they do with the numbers to get out?
Oh, they did this. They did what we're going to do. See what they're going to do now here? Because remember, we looked at the scatter plot. And it looks like there could be a linear correlation. It's negative. We do what? Use the 5% level of significance, right? So we're using this as 5% because I set it up that way, 5%. And it says that right here anyway in our instructions. And yes, we have 8 data values. So what's our degree of freedom if there's 8 data values? Remember, for linear correlation, it's n minus 2, the definition. So it's 2 less, not 1. And so that'll give us these critical values here. Okay? So I got my critical values. We set up our hypothesis, right? This is a setup. This is our decision rule. Now, to answer your question, you might say, oh, Mr. Judge, how do we get that R value? Let's get you guys back. So to get the R value, we're going to use this information here. So remember, I said write down all this stuff. So we have N is what? 8. Is that right? What's my sum XY?
1269.
What is it?
1269.
1269. Good. What's the sum x squared value? Sum y squared value. What's sum x squared?
2221.
2221. Okay. Sum y squared?
1025. Or 23.
Is it 1023 or 25? 23. Okay, good. We need sum x and we need sum y. What's your sum x?
129.
129. What's the sum y?
85.
85. Okay, let's plug these things in here. Remember, n is 8. Sum xy is 1269. Sum x is 129. Sum y will be 85. I'm going to plug them in next to these values. 8. And then that's going to be 2,221. Sum x is 129. Don't forget, you got to square that number. N is 8. Sum y squared was 1023. And then sum y is 85. And again, we're not going to forget to square these values. So I'm going to plug everything in here. So remember, I write it down again. 8 times 1269 minus 129 times 85 over square root 8 times 2,221 minus 129 squared. Square root again. 8 times 1023 minus 85 squared. So double check to make sure we have everything in the right places here, right? Looks like we do. And remember, I'm going to remind you guys that you're going to square that value. Okay? So you guys have that written down? All right, we're going to punch this in the calculator now. Okay, what's in my numerator here? We're going to compute that. 8 times, what's sum xy?
1269.
Okay, minus, what's sum x and sum y?
129 is sum x. And sum y is 85.
Okay, close that parentheses, divide by. Now remember, you're dividing by the product of two radicals. Remember this? So open this. After your division, put an open parentheses, because you're now going to say, hey, in the denominator, we're going to have to multiply two radicals. So I have the first radical here, and then under that is n, and I have sum x squared, so it's 8, right? 8 times what? What is it? 22, 21, minus, what's that sum x? I think, is it 129? And you're going to raise that to the second power. Is that right? Okay, good. Now, I have to get out from the radical again. So I'm going to use my arrow key. And now I multiply by the second radical. And then I answer 8 times now. What's sum y squared? What is it? 1023. Good. And then minus sum y to the second power. It looks like 85. Is that right? Double check. Is it 85? And then I'm going to come out of this and close the parentheses because I'm telling the calculator, okay, calculator, that's the end of what's in my denominator. What do you guys get for this R value? It's negative what? Isn't that negative 0.782? Now notice this value to the nearest thousandths, negative 0.782 here. Okay. Negative 0.782. That R value is close to -1, but it's not that close. It's actually pretty far. It's not even close in terms of probabilistic values, right? Remember, close is being within, what, 5%. So I'm going to look at this R value, and I highly suspect that, what's the deal? Did we get the same R? Yeah, we did. Okay. Notice we got the same R. But I highly suspect that there may not be a linear correlation because R is not really close enough to -1. Is that right? Well, let's see. What do we do next after we get the R value? We need the test statistic. Is that right? Negative 0.782 here, I replace for R. Negative 0.782. N was 8, I believe. Was N 8? Double check. Your test statistic should be negative 0.782 divided by the square root of 1 minus negative 0.782. Raise that to the second power over, was there 8 data values? I believe so. Wasn't there 8? Double check. All right, now can I replace this 8 minus 2 with just a 6, by the way? Would that bother anybody? Okay, good. So, let's compute this. Negative 0.782 divided by, now there's a square root there, right? Put the parentheses because you're saying calculator, I have a numerator here. Under the radical, there's a numerator. So I have 1 minus, open your parentheses and put negative 0.0782. You can close that and put second power here. And we forgot the decimal. Thank you. You know what it, yeah, okay. 782. Close that. Put your second power. Okay, good. Now, you're going to have to close this again. You say, why? Because you just told the calculator, I have a numerator under the radical. I am still under this radical because yeah, am I? Oh, no. Let me double check here. Okay. Well, this particular calculator, I can put divide by what? 6. This calculator, it puts you under that radical. To get out of the radical, I have to use the arrow key. So what you guys see is the numerator under the radical in that first set of parentheses, and then that's divided by 6. And it's saying that the 6 is still under your radical because it's not outside. So what is this test statistic value going to be? What is that? Is that negative what? Double check. Did we put the right values? So it's negative 3.073 to the nearest thousandths. Negative 3.073. So we'll say test statistic is negative 3.073. This is another number I need. And then I go back again and find where that is. Negative 3.7. What is this? Where is that negative 3.073? Is it past negative 2.447? What do you guys think? Is it? Yeah. So I guess there is. We reject the what? We're in the reject the null region, so reject the null. I guess there is a linear correlation, but I want to let you guys know it's really not a very strong one. It's a weak one. So anyway, if I actually use the original 1%, it might not be. And I think that was the intent. So anyway, I took these questions from another text, not your text. And the original intent of this was 1%. And I think they wanted to show, yeah, there's no linear correlation, but if you change it to 5%, then guess what? It's about there. So anyway, I just want to throw that out for you guys here. So if there is one, it's kind of a weak one. So this is my test statistic of negative 3.073. Let's now go through finding the equation, right? So I want to go back here and I want to remark here. Let's see what this might look like. Now if I go to chart, let's go to chart here. And I want to insert an element. I'm going to insert a trend line and it's linear. This is the equation they're talking about, so you guys know. Okay? So let me kind of follow that. Oh, that's weird. Undo. I don't know if you guys can see that line. Could you guys see that line? Right? There's the line they're talking about. So the data does kind of follow a line. It's really off that line. This is the best fit line. It's a kind of weak negative correlation, meaning a negative slope. And again, as we said, we need the equation for what? For this thing, we need what? Let's put it over here. Y equals mx plus b. So we're going to need to find that equation again. Okay, it does fit. Fine, so let's go through and find that. So as we've been doing here, let me summarize this. The R value is a negative 0.782. We've got a test statistic, negative 3.03. Negative 3.073. And our conclusion again is yes, we have a what? The data suggests that there is a linear correlation. However, I'm going to remark here that there's a weak what? Negative. So I'm going to start to give you guys a little more information about how you want to do this, how you think about this. So let's find the values here now. I need a slope, so I'm going to use my big eraser. And let's use our slope formula. So our slope formula for the best fit line, the regression line, remember M is N sum xy minus sum x sum y over N sum x squared minus sum x in parentheses squared. And here is 8. Sum xy is 1269. Sum x is 129. Sum y is 85. And here is 8 again. Sum x squared is 2,221. Sum x is 129. And don't forget with that 129, we have to raise it to the second power. Our slope here is going to be 8 times 1269 minus 129 times 85 divided by 8 times 2,221 minus 129 to that second power. So don't forget, you're going to put that second power here. I know I keep nagging you guys about that. Let's find out what that slope's going to be. All right, you guys okay with this? Let's find out what the slope is here. So, did you guys copy this stuff down? Did we do okay, an okay job for, did we locate everything okay? We're going to go to our calculator now. Okay, so let's get this value. This is 8 times, what's that sum xy value? 1269. Okay, minus 129 times 85. Close that. Divided by, what's n? 8 times, what's that sum x squared?
2,
Okay. And that's minus, what's sum x?
129.
129 raised to the what? Second power. So here's our second power key, is that right? Close that parentheses. Is that what we get? Is that negative, what's that, 0.721? Double check my arithmetic, ladies and gentlemen. Does that look okay? Okay. Negative 0.721, so negative 0.721. There we go. So here's the slope of that line. It's a negative slope. Okay? Now, how do we get the B value? We're going to use E like green. B equals some y minus m, some x over what? N. Is that true? Let's plug these values in. Some y, 85, negative 0.721, and 129, n over what? That's 8. So B here is going to be 85 minus negative 0.721. Let me see if I can fit this in here. B will be 85 minus negative 0.721 times that 129 over 8. Don't forget there's a decimal there. So make sure you guys write this down, and I'm going to remark, just so you guys know, using a little bit of algebra, let me bring up that topic. What's minus a minus? Is that plus? Okay, so I'm just going to throw that out there, because I can actually enter this in my calculator with a plus, but maybe I won't, so I don't want to confuse people, but I want to point that out. You guys okay with that? Okay, let's enter this here. What do you guys get here? You got a numerator, and let's go back. What do you guys have here? You got some y, right? What is that going to be? 85. Good. 85 minus what? What's your m value? Put your parentheses here, and put negative 0.0, or I'm sorry, yeah, 0.7. Didn't come out. 0.7, is that what? 21? Is that true? You guys okay with that? Close that, and then multiply that number with what? With the sum x? What's your sum x value? 29? Okay. 129, so go back here. 129, is that right? So isn't that my numerator? Close this, and then you divide by, what's the sample size? 8, good. So I don't know, I think this calculator is growing a bit on me. I think we get to see everything a little bit better. I don't know how you guys feel. Can you see it better on this calculator? Did you guys see everything better on this calculator, or is it just me? No? Let me see. Yeah, I think you can see things better here. Okay, what's this value to the nearest thousands? 22.251. So this value here for B is 22.251 here. All right, this is my slope and my y-intercept here. And let's write down that equation. So you guys have these values here? I think I'll write it down here just to kind of get this in my memory. So let's put it over here. Y equals, my slope is negative 0.721 times the variable x plus 22.251. So here is the regression line, or the best fit line. And if you wanted, go back and write it here. Remind me, what does y equal again? Negative point what? 721x plus 22 point what? What was the decimal values here?
251.
And so, ladies and gentlemen, take a look. It does look like it has a negative slope, and it does look like eventually your y-intercept would be about 22.251. So this can be used actually if you actually take the x coordinate value, which I believe is the is the number of what? Police officers, right? Yeah, the number of police officers in a particular area. If you increase X, what that means is your Y value will decrease, meaning the number of muggings will actually go down. Now that's a weak linear correlation. That's kind of weak. It's not strong. So, there's a degree of error associated with that. Okay, so you can't say that's 100% accurate or even close to 100% at all. It's not very accurate, but there is some correlation, somewhat weak, and it kind of makes some sense, in all honesty, to me. It's close to being a nonlinear correlation, actually. And if you change that level of significance to 1%, it wouldn't be. That's my guess. Okay, because 1% is a more accurate kind of test. It's a smaller level of significance. That's about one, probability of like 1 over 100. This is 5 over 100. So it's a factor of 5 there. So it's kind of weak, but you know what? Nevertheless, it worked out here for us. And I don't think that was the intent, but different books can use a 1%. Triola has moved away and done 5% for whatever reason. Well, you guys know the reason. To sell more textbooks. I should say new textbooks. So this little fine detail I've been, notating for you guys here is it's very real, So there it is here. So that's your line. So this here, how?
On the to get the R on the
Okay, over here.
Thank you.
And so this is the whole process, the complete process behind finding a linear correlation and a best fit line. All right, you guys okay with that?
Yes.
Okay, you guys good? Should we try another one? All right, let's have some more fun. Uh-oh, what's this next situation? Ooh, in honor of Thanksgiving. Woo! In honor of Thanksgiving, problem number 4, so you guys know. In honor of Thanksgiving, what does this mean for us? Let's see. Well, weight loss. The bivariate sample data below represents the number of weeks a person is on lose weight quick pills. And the cumulative weight loss in pounds, meaning, they're adding the pounds that you're losing. So if you said, over this period I lost 10 pounds, right, over a particular period, well, you didn't lose all 10 pounds in the first week. You didn't lose it in the second week. They added the weight loss. That's cumulative. So you got a cumulative weight loss. Fine. Use what here? What are they saying? Use the what? 5% level of significance to test the claim that there is a linear correlation between the two quantities. And yes, we put alpha's 5% there, okay? And it looks like our sample size is 7, so the degree of freedom is 5. Okay, we don't really care about that yet. We have to see if there's a what? I mean, should we even go through the test to begin with if we know the scatter plot looks random, that the data can't be necessarily modeled with a line? So we're going to go look at the scatter plot, okay? All right. So here we go. And then I'm going to do this here. So let's actually do this here. We're going to insert here we're going to look for a chart, and they want us to do a scatter, right? There it is. And I think before I do that, right, if you guys know, let's go back here. Before I do that, I have to highlight the data. Now I get to do what? Insert a chart here. So here's chart. Here's scatter. There we go. And I'm going to put it over here again. Okay, let's take a look at this. What do you guys think? Do you think we can actually, I don't know. Do you think the data looks like it might fit along a line? Can we find a best fit line here that can describe this data, you think, in some way? Notice that it's a positive slope if we could. So it looks like the data, I would say it looks like we might be able to model that with a line. So we're going to go through the process. We're going to find out. All right, you guys okay with that? So, okay, let's go through this process. Now, maybe, I don't know, let's see if we do this here. Does that work out okay? Can you guys see that a little better? Maybe not. Maybe let's undo that. I'm just trying to get some more space here. So, okay. This here has to be, let's enter what? Don't we have an XY column again? And then we have a what? X raised to the what? Second power? And then I have a what? Y raised to the second power? Okay. Let's get that out of the way. All right, now we're going to enter some things here. We're going to go here. Okay, let's try it again. Equals. No. Uh-oh. Sorry. Equals. Okay. This value.
You're gonna have all this on
Yes.
here.
This value, the same way it's on your study guide. Absolutely. And we'll talk about that later to reinforce the idea, because there might be people who don't understand. So here, where is that equal again? Equal. Okay. X raised to the second power, yeah, equals Y raised to the second power. Okay. We're going to do autofill. Okay, we got all that information. Now, don't we need all the sums? So let's do the sums now. So be careful here. Okay, so let's see if we can get out of this mode so we can see everything here, right? And then we're going to highlight everything here. Anyway, put that in. I think we like the light blue, right? So make sure, and at this point, let's actually increase the size here. Let's go out to what? 18. All right, so at this point, make sure you guys copy this data here. Okay, as you copy this, I'm actually going to compute the correlation here. Okay, so copy that. I apologize. All right, you guys okay with that? So what's this R value going to be again? It's approximately 0.89 what? 7. So let's verify that that's what we get. Okay, you guys okay with that? Let's verify this. Did you guys copy down all the information you need? Okay. So remember what you would do. You set up your what? Your hypothesis test. Since your sample size here is 7 here, right? The degree of freedom is 2 less, which is 5. And that's going to give you these critical values. So we put them here and here Remember, half of 5% is actually 2.5, so that's in the tails. And yes, you use the t-table here. So we set up our hypothesis. We're just going to now compute the R value in the test statistic and draw our conclusion. And if there isn't a linear correlation, we're going to find the slope of the best fit line, and we're going to find the y-intercept. So this is where the work's going to be here. So what was n again? 7. We need again sum xy. What was sum xy? What was it? 181? Is that what sum xy was? Really? What's sum x squared? 140? Okay, what's sum y squared? 285? 245. What's sum x? 28? What's sum y? 39? Double check these values, ladies and gentlemen. Is this what we got here for all those sums? So you guys want to double check that? Sum xy is 181. Sum x squared is 140. Sum y squared is 245. Is that what we wrote down? Sum x is 28. Sum y is 39. So we have 181, 140, 245. Okay, and then we get sum x is what? 28 and 39. Okay. All right, good. So let's plug these things in here. So, in here, 7, 181, 28, 39, 7, 140, 28 squared, 7, 245, 39. Don't forget, with those values at the end, you square them. That's a power 2. Okay, don't forget that. So R then will be 7 times 181 minus 28 times 39 over square root 7 times 140 minus 28 squared, 7 times 245 minus 39 squared. Okay. So double check all this because we're gonna enter that in our calculator now. Right? We're gonna punch that in the calculator. Okay. Okay. So parentheses, 7 times 181 minus, what comes next? What is it? 28 times 39. Good job. Divided by, we're computing the R value, right? So we're going to have to open a parentheses there. And you hit the square root. And then I'm going to have under the radical 7, and let's go back. 7 times, what's the sum x squared value?
140.
Was it 140? Okay, good. Right, and then minus, what's the sum x value? 28. Square that. So in this calculator here, we're under the radical. We have to come out by the arrow key, and then we say calculator, multiply that with another radical. So I'm going to have to look at the y values now, right? 7 times, what's the sum y squared value? 245. Okay. Minus, what's the sum y value?
39.
Is that 39? Is that a 39 value? Okay. Don't forget to square that. Get out of that radical and put a parentheses here. Double check. what's this value here? Isn't that to the nearest thousandths 0.897? So it's 0.897. Let's write this down. Is that what we said we'd get? Is that what Microsoft Excel said we'd get here? Looks like it's 0.897. So okay, we are on the right track. Good. Now we need to find the what? Test statistic. .897, and this is 0.897. What was our sample size again? 7. So the test statistic is going to be 0.897 over square root 1 minus 0.897 squared over 7 minus 2. So don't forget, 7 minus 2 is the value what? 5. So we're going to answer this in our calculators again, and we're going to approximate to the nearest what? Thousandths. Okay, make sure you guys have that down in your notes, because we're going to punch this in. Divided by square root, parentheses, 1 minus 0.897 to the second power here. Close that, and let's divide by, was it 7 minus 2? Was there 7 values? Okay, what's 7 minus 2? I think I'm awake a little bit. That's 5, right? I think I'm awake now. And what's the test statistic here? 4 point what? If we approximate this to the nearest thousandths, what's that going to be? 4.53 what? 8. .538. That's our test statistic. So where does that live in our decision rule? Isn't it to the right? Isn't that to the right of the critical value of 2.571? It's to the right there, right? So let's remark here. This is in the reject the null region. So when you reject the null, the null's gone. What does that mean here? Our conclusion is what? That there is a what? Linear correlation. So the sample suggests that there is a linear correlation here. The data can be fit with the best fit line. We now have to determine that best fit line. Okay, you guys okay with that one? So we're going to have to find the best fit line. Pretty good. Pretty good. Okay. Now, what I've been doing here is after I get this, right? Let's change the size of our array. Oh, it's still big. Let's actually find the slope of that best fit line, the regression line here. So we need the slope formula. M here is going to be, what's the numerator? N sum xy minus sum x sum y, everything over n sum x squared minus sum x in parentheses squared. Add your 7 here. Here's your 7. Sum xy is, isn't that 181 here? What's your sum x? 28. What's your sum y? 39. Is sum x squared 140? Double check. Sum x looks like it's 28, so double check everything. Seven times 181 minus 28 times 39 over 7 times 140 minus 28 squared. So we're going to punch this in our calculator. We're going to find out what that value is. Okay, you guys okay with that? So you guys have those values and verified that they're in the right place so we can actually punch that in? Okay, let's use our calculator here. All right. Okay, what's in my numerator here? What do I put? 7 times, what's the sum xy? What is it?
181.
181 minus,
28 times 39.
thank you so much. Ooh, that's weird. Let's try it again. It seems like sometimes if you, let's do it again here. 7 times, tell me what you have.
181
Minus,
28 times 39.
close that. All right, there's our numerator. Divided by, what's in the denominator? Anybody know? What do we put in that denominator now? 7 times 140 minus 29? 28 squared. Okay. So double check we wrote the right thing down here, right? If we double check here, I think we're okay. So this is our slope. It's about 0.892, or is it 893? Good. Round to the nearest thousandths, that's 0.893. So here's going to be our slope, 0.893. Do you guys have that down there? 0.893. So m approximately 0.893. So we're going to use our ELAC version. Is that what it is? The green version? That's a how to find the Y-intercept value. Oops, let's put it down here. Okay. This is a user-friendly version here. Okay, for your Y-intercept. And again, sum y, we have what, 39 here. M is 0.893. Sum x is 28, and our sample size is 7 here. (39) times 0.893. Oops. Let me go back. That's not what we have. 39 minus point what? 893 times 28 divided by 7. So let's find what this value will be. 39 minus 0.893 times 28 divided by 7. All right. You guys have that in your notes so we can punch this in?
No.
Okay. Okay, you guys ready to punch this in? All right, let's try this out. So parentheses here, right? What's the first thing we put here? What's the sum y value? Okay, 39 minus 0.89. Go back. 0.893, is that right? Times, what's the sum x value? Is that 28? Okay. Close that. And we get to divide by, I believe the sample size was 7, right? Okay. So double check, verify this. See everything is correct there, and it looks like it's about 1.999. 1.999. So this is 1.999. And what that means is our best fit line here will be 0.893x plus 1.999. So this is the line we could use to predict. Regression line, best fit line, it's the same thing. So let's make sure we write this down. Let's go back to Excel and say, okay, Microsoft Excel. You can add an element, Trendline Linear. Okay. Here's the regression line. Notice it has a positive slope. Okay, that looks like a strong, that might be pretty strong here, linear correlation. Might be strong. It's not perfect, but it's pretty good. It's a pretty good linear correlation. Positive slope, so it's a positive linear correlation, right? And notice that it looks like our Y-intercept would go through about 2. So we can now predict. So we can get an X value, and it'll give us a corresponding Y value. And maybe we should make this a little bit smaller, if we can. Anyway, it's a little bit smaller here. So could you guys see this line? Do we have to draw it? Do we have to draw a nice line for you in blue, maybe? Highlight that line. A little bit. I know it's a crooked line, so let's... There you go. There's the line. If you can't see it, it's right there. And there's your best fit line. Yes?
For the predictions, in the book it mentions that if the regression line is a little too scattered, if it's not as good.
Yeah.
I guess they mentioned to get the averages of the Y. And then if it is a good regression line for the prediction, all we have to do is like plug in like the X. My question is like, how do you know whether it's a good regression line or it's not? Like, is there like a limit? You're just like, hey, you know what, this is too scattered. The plots are too scattered.
Well, yeah, there's a lot. Okay, yeah. There's a lot more to what you're doing here. And the answer is yes, you can actually do a lot of other things here to kind of make this a better situation. But yeah, this is kind of a rough sketch of this idea here of what we do. But yeah, now as you have a beginning sort of elementary understanding of all this, then you could go further and start to say, okay, what can I now do with some of these things? And that's the whole idea. With a lot of other stuff. So, but let me I'll remark further about those here, but for the sake of the video, we'll kind of stop it right there, and I'll give you some more information here on that, okay? But yes, absolutely, absolutely.